Hey everybody, it's Mr. N here, and this is the 7-8 lesson from our textbook. It's on indeterminate forms and L'Hopital's rule. So let's go ahead and start off by some of the basics that we have talked about at the very beginning of the year when we did limits. Suppose we had some sort of limit we were taking and we ended up with an indeterminate form. So right here we had some sort of indeterminate forms like 0 over 0, infinity over infinity. And that was our indeterminate form. Well, we said, okay, here would be an example. If I plug in 1, I will get 1 minus 1, which is 0. 1 minus 1, which is 0. This is indeterminate. So at this point, we had said, okay, we need to factor. We need to try to clean this up and do this again. So I factor the top. I end up with x times x minus 1. So I took the x out. The bottom, this factors into x minus 1, x plus 1. And now I can reduce by taking these out right here. And I will go ahead and plug the 1 in, and I'll get 1 on top, and I plug the 1 in, I get 2 on the bottom, and the answer was 1/2. That's how we did it at the beginning of the year when we dealt with limits. We could do the same thing as we're going to infinity. If we have this, we end up with infinity over infinity. We plug it in here. This is infinity squared. This is that. But then we said, okay, here's a trick to it. It's the same type of thing, but we're going to divide the top and bottom by x squared. So the trick was just to look at the coefficients that were in front of the highest power, which is x squared. And that yielded 1/2. The actual process is to do the division. That part of it you learned in trig. But then in calculus we said, okay, this is x squared, that's x squared. Just take a look at the coefficients that are in front of it. It's 1 over 2. And then we can get a little bit crazy. What if we had this situation right here? You want me to use a little different pointer? I could use this one. What if we had this situation, or would you prefer this one? Okay, so what if we had this situation? Well, if I put in 1, the ln of 1 is 0, and but now I can't use any of these tricks. I don't have the 1/2 here. I don't have the same powers that I could just take the 1/2. I don't have anything that I could factor and reduce. And even if I went to infinity, this is also indeterminate. So the question becomes, what do I do when there's nothing, there's no tricks, there's no things to factor, none of that stuff? So what do I do? Well, there is a trick. And L'Hopital came along and he discovered this. So just real quick, L'Hopital, his background is he figured this out in somewhere in the 1690s. He had only lived like 40 something years, I think 43, 45 years total. So he was pretty young, like they all were. And he did work with Bernoulli and some of the other famous mathematicians. But he came across this situation and said there's got to be a way to be able to solve something like this. And so we end up with L'Hopital's rule. And he said, suppose f and g are differentiable and g prime of x does not equal 0 on an open interval I that contains a, except possibly at 0. And suppose that the limit as x approaches a of f of x equals 0 and the limit as x approaches a of g of x equals 0. So we have our f of x equation and our g of x equation. We're taking the limits of these and they are indeterminate. Or they are positive or negative infinity. So basically he's setting up this whole indeterminate situation with that first one. He said then the limit as x approaches a of f of x over g of x is going to be the same exact thing as the limit as x approaches a of f prime of x over g prime of x. So if the limit on the right side exists or is infinite or negative infinite. Wait, what does this mean? Wait. Let's back it up. Let's take a look at this. He's saying, look, if you can't do this directly and you get an indeterminate form, he said, okay, well then just take the derivative of the top, derivative of the bottom, and try it again. What? Wait, derivative of the top, derivative of the bottom, and try it again. So let's just do that on this example that we had right here. Okay? All right, so I got an indeterminate form, but now he's saying, all right, take the derivative of the top, which is 2x, take the derivative of the bottom, which is going to be 4x. These reduce, and I will get 1/2. What? Wait a minute. Wait a minute. Let's look at this. Okay, take the derivative of the top, which is 2x minus 1. Take the derivative of the bottom, which is 2x. Plug in the 1, and I'll get 2 minus 1, 1/2. What? Wait, so we've been taught all these rules for limits, all these things to do, such as factoring, right here, such as this little trick, when all we had to do was take a derivative. That's what L'Hopital said. All we had to do was take a derivative here, if it doesn't work out, and take a derivative here, and then try it again. So, wait, so this one right here, if we took the derivative of the top, which is 1 over x, that's the derivative of the natural log, took the derivative of the bottom is 1, this would give me 1 over 1, and I plug in 1, and I get my answer of 1. Well, I don't even have to plug in 1, it just came out to be that. So that is that limit. Interesting. Interesting. And it works. It works for all of them. So yes, I know you're upset at me that I didn't teach you this at the beginning, but, well, it's just baby steps to lead to this. So let's try this example right here. Okay, we always start when we do these by plugging it in what the limit. We get 0, e to the 0, minus 1, so we get 0 over 0. So this is an indeterminate form. So now L'Hopital says, all right, we take the derivative of the top. We have the limit as x approaches 0. Now I'm going to take the derivative of the top, which is 1. I'm going to take the derivative of the bottom, which is e to the x, and then this goes away. So now I plug in 0, and I'm going to get 1 over e to the 0, which is 1 over 1, and there's my limit. All right, let's move on to the second one. Okay, for the second one, we have the limit as x approaches 1 of this, so I plug it in. So I'll get 1 minus 3 plus 2 over 1 minus 1 plus 0. On the bottom, I get 0. On the top, I'm going to get 0. This is an indeterminate form. So let's go ahead and L-hop it. Yes, that's the how we say L'Hopital. We don't say it all the time. We just say we're going to L-hop it. So we will L-hop, and on the top, I end up with 3x squared minus 3. On the bottom, I'm going to end up with, that goes away, this will be negative 1 plus 1 over x, and I want the limit as x goes to 1. So I plug these in, and I will get 3 minus 3 over negative 1 plus 1, 0 over 0. This is another indeterminate form. Guess what I do when I get a second indeterminate form? I L-hop. I just keep L-hopping until it works. So L-hop again. So this time the limit as x goes to 1. This becomes 6x. On the bottom, this is, remember, x to the negative 1, so I'll get negative 1, x to the negative 2. Plug this in. I'll get 6 over, this will be, remember, this is negative 1 over x squared. I will get negative 1. So the answer is negative 6. There you go. That's what this limit is. If you don't believe me, graph it. Take a look at it. L'Hopital was right. So all we had to do on any of these was just L-hop, and it gives us the answer. Yes, I know your questions. Will it work for all of these? Yes, it will. So let's take a look at the next one. Over here, the limit as x approaches infinity. When I plug infinity in, this will give me a very big number over a very big number. So this is an indeterminate form. Guess what do? We L-hop it. So we'll have the limit as x goes to infinity, and on the top I get 1 over x, so I took the derivative there. On the bottom, I'm going to end up, remember, that's 2x. This is 2 times x to the negative 1/2, so I'll end up with negative, so be careful, this is 1, I meant that's 1/2. Okay, so I'll end up on the bottom here with 1/2 times 2, which goes away, and this will be x to the negative 1/2. So this becomes 1 over x, and the bottom we said was going to be 1 over the square root of x. If I clean this up, I'll end up with root x over x, which is really 1 over x to the 1/2, so 1 over root x. And as I plug in an infinite number, I'll get 1 over something really big, which is 0. All right. Moving on to the next batch. What do we have? What if we had indeterminate products? Well, if you have these indeterminate products like this, what you want to do is you want to rewrite them so that you have the situation where you have an f of x over a g of x. So, for this first one, we can rewrite this. And how do we rewrite this? Take a look. Since we have a product right here, x times this, I can rewrite this to say the limit as x goes to 0 from the right, and we're going to rewrite this to say ln x, and I can put this on the bottom 1 over x. It doesn't matter which one you put on the top and bottom, but it's easier for, in this case, if I just put the 1 over x on the bottom there. So now, when I plug in 0 from the right, I will get the ln of x as it approaches 0 from the right. This is going to be negative infinity. Just think of the graph, right? When you take a natural log graph, it's going to go like that. So the bottom 0 from the right is also going to be 1 over a very big number, which is 0. So I'll end up with an indeterminate form. So we can L-hop this, because this won't work out. I'll end up with an infinite 0 from the right, something really, really, really tiny, infinity, negative infinity over infinity. So we're going to L-hop it. So on the top, I take the derivative, I get 1 over x. On the bottom, I take the derivative, I get 1 over x squared. At this point, this can be cleaned up, and we'll say the limit as x goes to 0 from the right, and this, when you clean it up, was just going to be negative x. And 0 from the right, getting closer to 0 from the right means a really, really, really tiny number, so it's going to approach 0. All right, taking a look at the next one. Over here, when I tried this one, remember we did this one earlier in the year, and we had to do some sort of weird trick to it. But let's see. As x goes to infinity, I get infinity times, in this case, the sign of 1 over x will be 1 over a really small number, so 0. So I get the situation where I have infinity times 0, and that's going to be indeterminate. So we're going to need to L-hop this. But before we do that, we have to rewrite it. So technically I should have rewrote it before I tried to plug the limits in. But in any case, we have the limit as x goes to infinity, and we are going to keep the sign of 1 over x on the top and then move this to be on the bottom as 1 over x. Again, if you put this in, you'll see that you will get an indeterminate form, and that won't work out. You'll get 0 over 0 is really what you're going to get. This is why I said you should probably do this before plugging it in. And at this point, we'll L-hop it, and we're going to get the cosine, taking the derivative here, we'll get the cosine of 1 over x times our negative 1 over x squared, right, because we have to use the chain rule. And on the bottom, we're going to have negative 1 over x squared, which those will reduce, and I end up with the cosine of 1 over x, and I need the limit as x goes to infinity, which is the cosine of 0, which is 1. So let's move on to this next one. And on this next one, we will take a look at what we got. And we've got the limit as x goes to infinity of e to the negative x over x. So we go ahead and rewrite this. We're going to say that this is going to be root x over e to the x. So it's easier to take this negative and just put it on the bottom as a positive. When I plug this in, e to the x is e to the infinite is infinity, so I end up with infinity over infinity, which does not work. It's indeterminate. We're going to L-hop it, and on the top I will get 1 over 2 root x, right, because it's x to the 1/2, and on the bottom I will just get e to the x when I take this derivative. So I took the derivative of x to the 1/2. That's how I ended up with that, just in case you are wondering. And this gives me, as I plug in infinity, I will get 1 over, let's just put this on the bottom right now, and you can see what I'm doing. When I plug in infinity, I'm going to get 1 over a really big number, right, which goes to 0. All right, let's take a look at what we got next. Indeterminate differences. Suppose we ended up with infinity minus infinity, which is bigger, infinity or negative infinity. We cannot tell, so this is another indeterminate form. So for these, we need to change it again to be something similar to 0 over 0 or infinity over infinity, and follow the steps as before. And we could do this by typically finding a common denominator, rationalizing it, etc. So let's take a look at this first one. So for this first one, we have the limit as x approaches 1 from the right of 1 over ln x minus 1 over x minus 1. All right, so we go ahead and we try the direct substitution approach. So we always try direct substitution, and I plug the 1 from the right end. I'll get 1 over something really small minus 1 over something really small, which is infinity minus the infinity, and this is our indeterminate form. So we're going to have to rewrite this. So we rewrite this, and here's what I'm going to do. I'm going to say the limit as x goes to 1 from the right, and I am going to go ahead and find a common denominator. The common denominator here would be x minus 1 and then the ln x. So I end up with the top as being x minus 1 minus, over here, ln x. And if I plug in 1 from the right, I get 0 over 0, which is also indeterminate, just to show you that up above it came out to be the same. So what am I going to do? I will L-hop it. I won't really bother putting things together right now. I will just go ahead and L-hop it. On the top, I'm going to end up with 1. This goes away, minus 1 over x. On the bottom, so I took the derivative of the top. On the bottom, I'm going to have to use the product rule. So first times the derivative of the second, plus the second times the derivative of the first, which in this case will just be 1. And let's take a look at what we have. This ends up being 1 minus 1 over x. On the bottom, I have this 1 minus 1 over x, if I distribute here, plus my ln x. Again, when I plug in the limit as x goes to 1 from the right, I get 0 over 0, another indeterminate form. So what do? I L-hop once again. And let's put this up over here. So I L-hop once again. I'm going to get on the top this time, that goes away. I will get the derivative is 1 over x squared. On the bottom, I will get 1 over x squared plus 1 over x. This all cleans up. When I put in 1 from the right, I'll get 1 over 1. On the bottom, I'll get 1 over 1 plus 1 over 1. When I substitute this in, the limit, and this all ends up as being 1/2. Okay, moving on, and now we've got indeterminate powers. So if we have any of these situations, f of x to the g of x, and the limit as x approaches a. If they are both 0, you have the type 0 to 0 power right here. And if you've got one as being infinity, the other as being 0, this is infinity to the 0. This is also an indeterminate power. And then 1 to either plus or minus infinity, 1 to the infinite, or negative infinity is also an indeterminate power. So all these are indeterminate powers. To be able to solve one of these, we just take a natural log. So ln y equals g of x times ln f of x, in this case, if our g of x was up here, because this gets moved down. And then we rewrite this, and then we solve it from there. And we'll have to most likely use L'Hopital somewhere in the mix there. All right, so let's go ahead and give a couple of these a try. So for this first one, we have the limit as x goes to 0 from the right of sine x to the x power. So we work this out, and let's take a look. If I were to directly plug this in, I have y equals sine of x to the x, and if I put in 0, I'll end up with 0 to the 0, and that's an indeterminate type. So I've set it up as y equals this, and we're going to take the natural log of each side this time, because that's what we had said in our steps. If you have an indeterminate power, take the natural log. So I'll leave that up here so you could see that. And let's go ahead and do that. So on the left side, I will end up with ln y equals x ln sine x, right? I brought the x down. So now we want the limit as x approaches 0 from the right, and we're going to take a look at this x ln sine x. So working this out, I get the product one, right? So I'll end up with this. If you look at it directly, it's 0 times negative infinity. If you rewrote this, we would end up with ln sine x, and I'm going to put the 1 over x on the bottom like that. And if I plug in 0 from the right, I will end up with negative infinity over infinity, which is an indeterminate form. So we'll go ahead and L-hop it. So we will L-hop this, and we end up with the cotangent, because this is going to be 1 over the sine of x. So I'm just going to write it as the cotangent of x, and on the bottom I will get negative 1 over x squared. If I rewrite this again, I can say that this is negative x squared over negative tangent x. I'm just putting it in stuff that you can understand. And if I put in the limit as x goes to 0 from the right, in this case I'll get 0 over 0 again, which is indeterminate again. So guess what I do? I L-hop again. So we'll L-hop the second time, and this time I'll get negative 2x on the top. So I took the derivative of the top there, and the bottom I'll get secant squared x. And when I take the limit as x goes to 0 from the right, this will end up being a very small number over infinity, so this is going to give me 0 in this case. So here's what I do with this. I know that this side right here, let me point it out, this is what the 0 was, because that was where I took my limit. So what I can do at this point is I can set this equal to it. So we're going to say that the natural log of y equals this 0. And we could solve it from here. So in other words, take e, so y will end up being e to the 0, which is 1. Let's go ahead and do another one to see if we can continue on with this. Maybe you can go ahead and pause the video and try this one on your own if you want to, but I'm going to walk you through it. So if we put direct substitution into this, direct substitution, I will end up with the infinity to the infinity type. So that won't work out. So what we need to do is we need to take the natural log. So I'm going to set y equal to 1 plus x to the 1 over x. ln y equals 1 over x ln 1 plus x. Remember, you do this whenever you have these powers. I'm going to rewrite this side right here because this is the side I'm going to take the limit of. So I'm going to rewrite this as ln 1 plus x over x. This is indeterminate. As I plug in infinity, it won't work out, right? Because you'll get infinity over infinity. So it's indeterminate again. So LHOP it. We LHOP, I get 1 over 1 plus x. On the bottom, I'm going to get 1. So this ends up being the limit as x goes to infinity, right? You could just say that this is 1 over 1 plus x. So this ends up being 0. And I can take my equation from here. ln y equals 0. And I end up with y equals e to the 0 again, which is the same limit as the other one, which came out to be 1. And let's go ahead and do our last one over here and see where we end up. And we have the limit as x goes to infinity of this. If I do the direct substitution approach and plug infinity in, I will get 1 plus 1 over infinity, which is 0, to the infinity. So I get 1 to the infinity type. And we know that this is indeterminate. So we need to do, since this is a power, we do the natural log. So y equals 1 plus 1 over x to the x. ln y equals x ln 1 plus 1 over x. And we work with this. And we're going to say the limit as x goes to infinity of this part of it. We know that this is going to be indeterminate. And I'm just going to go ahead and rewrite this, though, as ln 1 plus 1 over x over 1 over x, like that. And I know that this will be an indeterminate 0 over 0. So I will LHOP it. And I will end up with 1 over 1 plus 1 over x times negative 1 over x squared, right? I had to chain rule this part right here, right? I had to chain rule that. So let me just remove the markings that I made right there. So I chain ruled that, and then on the bottom, I'm going to get, when I take the derivative, negative 1 over x squared. Well, these will reduce out quite nicely. So I'll have the limit as x goes to infinity of this 1 over 1 plus 1 over x. And when I plug this in, I will get 1 over 1, which is 1. So now I continue on with what I had above. We knew that ln y this time is going to be 1, e to each side, so e. So y will equal e to the first power. And that's my answer to this. All right. Let's take a look at one last thing, and this is Cauchy's mean value theorem, and we can apply what we just did to the mean value theorem. And so it says, suppose that the functions f and g are continuous on this closed interval and differentiable on the open interval, then there is a number c such that, this was the mean value theorem, remember that? But, well, not kind of with a twist, and g prime of x doesn't equal 0. So what we're saying now is we can apply it in a similar manner by taking the derivative here and the derivative there of these. So Cauchy's mean value theorem is used to prove L'Hopital. So this is how L'Hopital's theorem worked out. Cauchy came along and he actually proved it, and it extends the mean value theorem to two functions. So really what this whole thing is doing is it's extending it from one function in the mean value theorem to two functions. Here was our mean value theorem. There's a little error in this. Make sure, let's fix it. This should say, for the mean value theorem, this should say f prime of c. The slope is equal to the average. Okay, so let's do an example with this right here. It says find the values of z in the interval 0 to 1, satisfying the conditions. And taking a look at this, here's what we got. We have f of x is that, g of x is that. And we want to satisfy the conclusion of Cauchy's mean value theorem. So we need f prime of x, and that comes out to be 6x 6x plus 3. And we need g prime of x, and that comes out to be 3x squared minus the 4. All right, so we need this on the interval from 0 to 1, as mentioned right here. So we need f of 1 minus f of 0 over g of 1 minus g of 0. And we need to satisfy this. Remember, we're finding z, so I need to plug f prime of z in here, so I get 6z plus 3. I need to plug g prime of z in here, so I'll get 3z squared minus 4. And why did we do that? Because that's what it told us to do. We have f prime of this value over here, and g prime of that value equals these averages. Okay, so that meant this right here would equal 6z plus 3 over 3z squared minus 4. Now, f of 1, let's find out what f of 1 is. F of 1, I plug it in, I get 5. F of 0, I plug it in, I get negative 1. G of 1, I plug it in, negative 1, and g of 0, I will get 2. So this ends up being 5 minus negative 1 over negative 1 minus 2 equals 6z plus 3 over 3z squared minus 4. And I go through and I cross multiply. And let's see, over here I'll get first 6 over negative 3 equals this. I'll cross multiply and I'll end up cross multiply, combine like terms. I'm just going to give you the basics here, right? Because if you cross multiply, you get 18z squared minus the 24. And then this equals negative 18z minus 9. Combine like terms, do all that stuff, clean it up. You'll end up with 3 times 6z squared plus 6z minus 5 equals 0. So now what we can do is we can take this right here and apply the quadratic formula to it to solve for the zeros, and I will get z as being 0.54083. And this is the only answer that's in the domain from 0 to 1. So if you get multiple answers, just look for the one that's in the domain. And there we go. So hopefully this helped. I will give you more. Go through and do these problems. Just double check that you know how to do them, and I will give you more worksheets as time goes on. So thanks for watching, and as you guys always want me to say, hit that like button, smash the subscribe, put the notifications on, and see you guys soon.